Yeah, sure.
Нет, здесь не видно. Я говорю, я не знал.
Oh, Zohar, the microphone is here.
So Zohar will be talking about the unitary puzzle and fermions problems.
Thanks so much. I'm very happy to be here, learning new stuff every day. In particular, I also changed the topic I'm going to talk about because I found out a small issue with what I wanted to present before. And also yesterday I found out that Thomas knew about this issue and didn't tell me. So yeah, it's something I'm going to talk about something else, which is more likely to be correct. So yeah, it's based on a paper from a few months ago about line operators in gauge theory. I will just touch upon some issues in that paper, issues that are related to that paper at the end, and mostly some work in progress with Marieke, Van Beest, Philip, Boyle-Smith, Diego Del Mastro, and David Tong. And also I'll present some stuff that is kind of neither in neither of those two collaborations. So there will be three parts. All of them are very basic and nearly trivial. One of them is the unitarity puzzle in theories in 2 dimensions. This is some particular class of models that condensed matter people have gotten interested in recently. So I'll explain the unitarity puzzle in 2 dimensions. Then I'll explain the unitarity puzzle for fermion scattering in 3+1 dimensions. And a better understanding of the story in 2 dimensions would shed some light on this old problem in 4 dimensions. And then I'll discuss at the last part of the talk of are there any fermion zero modes to begin with around magnetic monopoles. So this will be the 3 parts, and they're all very basic. So let me start with a model that has been quite popular in some condensed matter literature recently. So they call it the 3450 model. It's just a theory of free fermions. It's completely trivial in some way. So there are 2 left-moving fermions, free complex left-moving fermions of charges 0 and 5. Those are moving to the left. And 2 fermions of charges 3 and 4 that are moving to the right. So it's a free Lagrangian of 2 complex left-moving, 2 complex right-moving fermions. And the charges 3, 4, 5, and 0 are chosen so that the sum of the squares of the charges of the right-moving and the left-moving agree to 25. And therefore, this model has a non-anomalous U1. So the U1 that assigns these charges 3, 4, 5, 0 has no 't Hooft anomaly. Furthermore, the number of degrees of freedom that are left moving and right moving is the same. So this theory also has no gravitational anomaly. So it looks a little bit like a chiral theory. It's just a theory of free fermions. There is no dynamical gauge field, but it looks a little bit chiral in the sense that the charge assignment is non-symmetric between left and right. Yet the charge assignment is done in this way so that there are no anomalies for neither the U1 nor is there a gravitational anomaly. Okay, so this is called the 3450 model. No, you cannot write any mass term that is compatible with the symmetries, obviously. Okay. Now, people in the community believe widely that every consistent quantum field theory, which has no gravitational anomalies and some symmetries G are non-anomalous, I mean no 't Hooft anomalies, there should be some way to continuously connect it to a gapped phase, which preserves the symmetries G. So in this model, obviously you cannot drive it to a gapped phase by adding masses, but you can add quartics, sextics, go to some UV fixed point, and then that UV fixed point might have new deformations that take you to a gapped phase. And this has been shown explicitly in this model on the lattice by Xiaogan Wen and Juven Wang and Xiaogan Wen. They've done it on the lattice. They constructed a gapping mechanism for this model through some UV fixed point. Continuously, I meant, of course, going through some UV fixed point. So oh yes, there is a phase transition. By continuous, I meant something in the space. I meant continuous in the sense of space of theories. So if you ask a given theory A and theory B, can they be connected by any operators? If they can, I would call it, we can say that they're in the same connected component. So I meant continuous, that the theories are in the same connected component. I didn't mean that you can go to that phase without a phase transition, of course, because this is gapless and that is gap. So yeah, I just meant that there is some way to gap it out by some irrelevant and relevant operators. No, this is not allowed. Only deformations. Only deformations. No, the rules of the game is that you say theory A and theory B are in the same connected component if you can add operators to go from A to B. Now, it's not a semantical discussion. I'm just saying that in this model, people have found a way to do that. It was done on the lattice. I can also tell you how to do it analytically in continuum quantum field theory by adding some sextics, playing some Grosvenor type games, understanding where it goes. So, okay. So this is known to be true in this model. And if you can go to a gapped phase, there is a very nice bonus. If you know that this theory is connected to a gapped phase, it means that it also has a boundary, because you just go to a gapped phase in a half of the space. So you start from this model in infinite space, you go to a gapped phase in a half of the space. That guarantees that there is a boundary that preserves all the symmetries. So we have this picture. So this dot is not Lagrangian. You cannot write down the boundary conditions here in terms of the microscopic fields. It's a slightly non-Lagrangian boundary, but it exists. We know that it exists. It was constructed. I can construct it later if you want in detail later. So it just gaps the model in a half of space. Okay, so there is a boundary that preserves the U1 and preserves energy conservation. So there is an energy conserving boundary and a U1 conserving boundary. Yeah. No, it's a half infinite. It's a half infinite. There is a boundary that preserves all the symmetries in this system. One boundary, yes. Okay, so it's non-Lagrangian, obviously. You cannot write, you cannot say that it's Neumann or Dirichlet or psi. That wouldn't make sense. First of all, in this model, if you gauge the U1, it would not gap it out, because as you see, the central charge is 2, and you gauge only one U1, you'll have a massless field. So gauging doesn't gap this theory. But in the same spirit, you're basically right, that if you want to create boundaries, you can try to gauge in a half of space. But it's not important for this discussion. All you need to believe me is that there exists a non-Lagrangian boundary. it has G equals square root of 5, where G is Dafleck Ludwig boundary entropy. So it's somewhat non-Lagrangian if there's a square root. Okay. So if such a boundary exists and you believe that it exists, it raises an interesting puzzle, because let's say I make a wave packet out of this fermion. I make a wave packet of the charge 3 fermion and I send it in. What can possibly come out? Because the outgoing states have charges 0 and 5, and you cannot make charge 3 out of 0 and 5. So it raises an obvious unitarity puzzle. So that's what it says here. If you make a charge 3 from the left, how can you get something to come out? So this is an obvious puzzle. It's called the unitarity. We call it the unitarity puzzle. Great suggestion. Great suggestion. So there is a theorem that for boundaries like that, so there is a theorem that conformal boundaries in 1 + 1 dimensions, it cannot store charge or store energy. This is called the Cardy condition. You can verify that this boundary satisfies the Cardy condition. And the physical meaning of the Cardy condition is that all the momentum that comes in comes out, and all the charge that comes in comes out. So therefore, conformal boundaries cannot store energy or charge. So therefore, there is a very sharp unitarity puzzle in this model. Okay. It's actually, yeah, in the Maslow-Schwinger model, there is a similar puzzle. And I wouldn't say that this puzzle is terribly somehow new. It might remind you of the deconfinement in the Maslow-Schwinger model. It might remind you of things, but this is extremely elementary. It's a theory of free fermions. So if we must be able to solve it here in detail. Well, but you still have to find what wave packet is going to carry charge 3. So you're not going to get away without that. Okay, so I'll tell you the solution, and then we'll go up in dimensions to say that the same solution holds. So there are actually many possible boundary conditions which preserve the U1 and energy conservation. Nobody classified these possible dots, so we don't know the full space of boundary conditions. And the answer might depend on which one you pick in particular. The one that was constructed in the literature by Wang and Wen and by David Tong and by others preserves an additional Z5 accidentally. So you have the U1 or the original U1 that is preserved by the boundary, but there is an accidental additional Z5 that is preserved by the boundary that was already constructed in the literature. This Z5 acts in this way on the right moving fermion, on the fermions. So these are the right moving and these are the left moving. And the fact that you can preserve this accidental Z5 is because you can U1 times Z5 has absolutely no 't Hooft anomaly. So there is no obstruction to preserving this additional Z5. So people accidentally wrote a boundary state that preserves this additional Z5 because there is no obstruction to not preserving it. Not classified. We have one example. We have a concrete non-Lagrangian boundary that preserves U1 by times Z5. There is no obstruction to not preserving the Z5. The puzzle exists whether or not you preserve this additional Z5. Okay. So the paradox is resolved if you actually do the computation. You start from a wave packet, you evolve it. The paradox is resolved with this picture. So what comes out is not a state in the Fock space. It's attached via a tensionless string to the boundary. And the point at which it is attached will be very important. It's actually topological. So there is no energy or charge at the attachment point. Okay, so the outgoing state is not an actual Fock space state. It's attached by a string to the boundary, a tensionless string. So when you're an experimentalist, if you measure the outgoing state, you would see a state of charge 3. But would you as an experimentalist be able to see that it's actually attached to a string? It's not so easy. It's not so obvious how an experimentalist would see the string. There is a suggestion by Lin and by this. There is a suggestion in this paper that perhaps some out of time ordered measurements could detect the string, but it's not obvious how to detect it. This string generates a Z5 symmetry. It's a topological tensionless string that generates the Z5 that we accidentally preserved. Yes. Yeah, yes, I agree. I'm just, okay. So a crucial point here is that this line ends topologically on the boundary. So you can move the endpoint as much as you want. It doesn't cost energy or charge. You don't create energy or charge in this way. That exactly answers Arkadi's question. That guarantees that the energy comes out and the momentum, so the momentum comes out and the charge comes out. So nothing is stored. That's what I told you before. No, the boundary is simple in the technical sense. It has only one vacuum. There are no degenerate states on the boundary. You see what I'm saying? It's simple in the technical Cardy sense. There is no degeneracy on the boundary. Okay. It's an operator that's attached to a line. It's not a local operator. So it's not in the Fock space of outgoing states because those states do not create lines. There is a more abstract operator that creates a line. Yes, you can write it down. So let me just flesh how it works. So there are 5 topological lines like that. They generate a Z5, just a second. And this is the charges that they contribute to the endpoints. So this line contributes some exotic charges to the endpoint. And that's how the scattering works. With the charge that's carried by this line, the endpoint of the line carries some exotic charge. You can do the scattering. So let's go back to the scattering of charge 3. It turns out that you emit a line, a fermion of charge 5, and 1 fermion of charge 0. So you actually get kind of a composite state in some sense. You get at the endpoint of the line plus 2 fermions, and that's the outcome of the scattering experiment. And it matches all the quantum numbers. If you're super quick in your head, you can check that all the quantum numbers match. So this is for this particular boundary. Yes. It's not, so, people often say that there is no S matrix in massless theories. I never understood what they meant. But one thing that they might have meant is that maybe the outgoing states are not in the Fock space. And this is a very clear demonstration that the outgoing states don't have to be in the Fock space. They are attached by tensionless strings to the point of scattering. Which state? Yes, but it has to be attached by something. Boundary plays an important role because it can end on the boundary with a topological endpoint. No, but I'm doing the theory in half space. At infinite space, it will be accompanied by something that's going to the other side. It has to end on something. The line has to end on something from the other side. With a boundary, it can end up, huh? Yeah, maybe not fermion. It might end on some other exotic excitation. Yeah, then it's a different story. No. So there are, even without a boundary, there are exotic states which can be at the endpoints of this line, but then one is moving right, one is moving left. And okay, it's a different question. If you hit the vacuum with the local operator, you might create it. You might create such a thing, but it's not an S matrix question. Okay, with a boundary. Okay, so I just told you so the solution for this class of boundaries that have been written in the literature is what I said. There are also probably some boundaries that don't even preserve this Z5. If the boundary does not preserve this Z5, then it cannot end topologically on the boundary, and the solution is not known. It probably involves some new tensionless lines. We know now that many, even simple theories of just free fermions have tons and tons of tensionless lines, tensionless strings, and probably they're important for the scattering problem for more general boundary, but we cannot make it precise. We don't know how to write down these boundaries. Okay, this is the end of the 1 + 1 dimensional story. An analogous story arises from scattering from monopoles. This is an age-old problem. I'll review it quickly. I believe nobody has ever said the answer correctly. So I'm going to use this 1+1 dimensional analysis to tell you the answer from scattering of an electron from a monopole, because the problem is essentially identical mathematically. So in this part, I'll completely neglect. How much more time do I have? I just don't know when I started. Oh, great. So I'll first completely neglect gauge field fluctuations, and I'll treat the magnetic flux as a background gauge field that doesn't fluctuate. So we put a monopole of charge little n, and we scatter a fermion of charge little q. The familiar result, of course, classically, when you scatter a charged particle from a monopole, it's reflected. It's called the mirror effect. It's in high school. Quantum mechanically charged fermions can plunge in. Charged fermions can get all the way to the core of the monopole because there is this mode with the reduced angular momentum, and it can scatter off the core of the monopole. And these are the fermion zero modes that are guaranteed by the index theorem. The physics of these zero modes is effectively two-dimensional because they just propagate in the radial direction and depend on time. And on the sphere, they are in a particular angular momentum channel, so they don't fluctuate on the sphere. So it reduces to a 2D problem, which is essentially identical to what I told you. There are incoming fermions, outgoing fermions, and the rule of the game is that for every wild fermion in 4 dimensions with positive Q, we have outgoing states in my condition, and for negative charge fermions in 4D, we have incoming states. So NQ incoming states and NQ outgoing states from every wild fermion with positive Q and negative Q, respectively. So the incoming states and the outgoing states might be different, but you can ask, are the anomalies cancelled, 't Hooft anomalies? So you check the U1 gauge anomaly, and you check the gravitational anomaly. So for this system to preserve the two symmetries, these equations have to be obeyed, and they are obeyed if the original 4-dimensional theory is consistent, if it has no anomalies. So this is mathematically identical to the 3450 model. For some choices of charges in 4D, you can get chiral gauge theories for these fermion zero modes. And the monopole is just a boundary. The monopole is a boundary at r equals to 0, and we scatter off the monopole. So if you bought the story I told you in 1+1, it's essentially the same. I'll show you an example. Let's say that we have an F fermions. Let's say that we have QED with an F species of massless fermions in the fundamental, and these are the gauge charges. This is just a simple version of QED with an F species that arises from the GATT models and from Seiberg-Witten theory. So people would say that the boundary condition at the monopole is that the incoming fermion is reflected to the outgoing fermion. This is a simple Lagrangian boundary condition that preserves U1 gauge, but it obviously violates SU and F because the incoming fermion is in the fundamental, and once you take a dagger of Psi-Twiddle, you get an anti-fundamental. So clearly, the monopole boundary condition has to be non-Lagrangian if you want to preserve isospin symmetry and charge conservation. And theta is like theta was just a free parameter in the literature when people discuss monopole boundary conditions. But of course, it has to be a non-Lagrangian boundary. Let me just say that this naive boundary condition only makes sense when the monopole charge is 1 and the number of fermions is 1. Then it conserves all the symmetries because there is no isospin and there is no axial symmetry. For any other choice, this boundary condition doesn't make sense, and you have to write a non-Lagrangian boundary condition, like in the 3450 model. So this boundary condition with a theta angle only makes sense in some special case. No puzzle, it's just the phenomenon that is called helicity flip, that an incoming fermion, the direction of the helicity is flipped by the scattering. But there is no puzzle. And there is no puzzle for other values either. You just have to have the monopole is a non-Lagrangian boundary condition. So the monopole is a non-Lagrangian boundary condition. There is a puzzle with scattering because we have incoming fundamentals and outgoing fundamentals, but we have to complex conjugate to preserve the gauge symmetry. So we cannot match the quantum numbers. It's exactly like in the 3450 model. And the solution is, as before, we have to have a topological surface that comes out. So this is the picture. I'll spare you the details. So our suggestion is that the actual solution for the monopole scattering problem is that the incoming electrons are just ordinary wave packets, but what comes out is a topological surface. And at the end of this topological surface, there are the outgoing radiation modes that you actually measure in an experiment. So actually, interestingly, this is probably something that wasn't mentioned in the literature. When we analyze which topological surfaces come out, some of them carry a quantum Hall state. So they're not just tensionless, benign topological surfaces. They actually carry some vacuum degeneracy and topological excitations. So this is the story of scattering from a monopole when you neglect gauge field dynamics and you just study the zero mode scattering. So of course, this is a version of what was called the Kallan-Rubakov effect. What is Kallan-Rubakov? Kallan-Rubakov was the observation that there is some scattering, there is some puzzle in scattering, and they said that the outgoing radiation has fractional quantum numbers. Now here, there are no fractional quantum numbers. It's like in the 3450 model. All the quantum numbers are integer, but there is a topological surface. So that is, in my opinion, the correct resolution. So there is nothing fractional, no quantum numbers that are conserved in the scattering experiment are fractional. It's just that there is a topological surface that comes out. This is a different problem about the magnetic field that's constant in space. I'm not talking about it. I'm talking about scattering from a monopole. The quantum numbers are all integer. There is no fractionalized quantum numbers, but you have a quantum Hall state that comes out with the radiation. Okay, so this is the comment I had about monopole scattering. It's an open problem to actually write the full monopole boundary conditions that preserve all the symmetries. In many cases, it's not possible. There are some groups working on that now. Several groups are working on that now. Okay, now I'll come to the last thing I wanted to tell you, that we've ignored so far the monopole dynamics, the gauge field dynamics, and we discussed the fermion zero modes, which just have this very simple Lagrangian. This is literally the Lagrangian of the fermion zero modes. If you ignore gauge field fluctuations, there are incoming states, outgoing states, and they are protected by the index theorem. So, but if you think about it, more deeply, what actually protects these massless zero modes of the fermion? It's a very famous fact that we learned that there are fermion zero modes because of the index theorem, but there aren't actually that many symmetries in the system. All there is one for magnetic symmetry that protects the magnetic flux, and there is a small axial symmetry that depends on the monopole charge. That's certainly not enough to protect these fermions. So let's consider a very simple toy model to understand the fate of these zero modes. We have magnetic flux through the S2. And then using the index theorem, we conclude that the Dirac operator has n zero modes. And people say that the gauge field fluctuation doesn't matter because this integral is topological. So there should be fermion zero modes. However, this discussion is imprecise because there are also gauge field fluctuations in the two directions that are transverse to the S2, AX and AT. So the actual 2D zero modes are coupled to the gauge field fluctuations in the directions transverse to the sphere through which there is a magnetic flux. And you get this model instead, if you consider gauge field fluctuations. So the gauge symmetry, so basically U1 gauge is gauged, and there is a two-dimensional gauge field that couples to the zero modes. This gauge field, all the symmetries of the system are just a ZN axial symmetry, where little n counts the number of fermions. And here I'm assuming that we'll only have one species of fermions, so no isospin symmetry for simplicity. So the symmetries of the system that are exact in the full UV theory are just a ZN axial symmetry and the rotations of the sphere. And the fermions are in a spin n-1/2 representation of the rotation group. So this is a very simple 2D model. It's like the Schwinger model. And we know what it does. It gaps out one of the combinations. So we bosonize this model, and we see that this combination, which is the sum over the bosonized degrees of freedom, is gapped out. So therefore, therefore, the number of zero modes is not correctly captured by the index theorem. So when the mass scale that we generate from the Schwinger model is the electric charge over the radius of the S2, which is much smaller than the KK scale. And we have a very interesting vacuum expectation value around the magnetic monopole. We take a product of all the fermion zero modes, and they are left moving and right moving. This has a non-zero expectation value. That's what we found by analyzing the gauge field fluctuations, how they couple to the fermion zero modes. This VEV preserves the rotational symmetry, and it preserves the axial symmetry, and it preserves the gauge symmetry, but it gaps out some of the fermions. It doesn't gap out all the fermions for little n. It gaps out one linear combination of them. But there are many dangerous quartic interactions that I don't know what their eventual fate is, but possibly many of the fermions are gapped, or all of them are gapped. For now, I'll just concentrate on little n equals 1. We see that for little n equals 1, which is the simplest, which is the minimal monopole flux, there are actually no fermion zero modes. Okay. So many people have recently considered various 2D models like that, starting from Gross-Navet, and many others considered recently the effects of quartic interactions and gauging. And clearly, this is a very relevant problem to understand the zero modes around the monopole, because analyzing those might lead to the conclusion that all the modes are gapped, at least for an f equals 1. So for n equals 1, we see that there are no fermion zero modes, and what used to be the fermion is a kink in the Schwinger model. But we know that the Schwinger model is deconfined. So actually, when you put a fermion, it creates an anti-fermion, and they form a meson, and there is no confining string to the next one. So these phi mesons are formed so instead of the zero modes, we have massive phi mesons, and there is no force between the phi mesons. So we must now revisit the scattering problem. Does it even make sense to talk about the scattering problem, given that there are no zero modes? So the equation of motion that you would get, now we learned that there are phi mesons instead of zero modes. And these phi mesons, since they have a mass, there will be a centrifugal barrier to scattering an electron from the monopole. But now the centrifugal barrier, this is the equation that you'll have to solve. This is the differential equation. And what this effect that I told you leads to is the conclusion that the phi meson decays near the monopole. It cannot plunge all the way in. So you might have heard that massless fermions can plunge all the way to the core of the monopole and scatter, at least in this lowest angular momentum channel. That's not true. They actually, the wave function decays, they cannot plunge. There is a centrifugal barrier because of the effect that I showed you. This is the ordinary boundary condition that people imposed for little n equals 1. That's what I told you before. It had a theta angle, and it assumed that the fermions can plunge in. The correct answer is that there is no theta angle. So this theta angle, about which there are probably 1,000 papers, doesn't exist. There is no theta angle in the boundary conditions. There is a centrifugal barrier. And in the language of defect conformal field theory, if you think about the monopole as a 't Hooft line and it has to have conformal invariance, this is tantamount to saying that there is no marginal operator on the monopole. So this theta angle was interpreted in the literature as a marginal operator on the defect, which is the monopole, but such marginal operators don't exist. They have an anomalous dimension, which is e squared over pi. So is there a scattering puzzle, given that the monopoles cannot actually plunge in? I think the answer is yes. Even these phi mesons still lead to a scattering puzzle. So this picture that I showed you at the beginning is still correct. You still need to emit a topological surface in the scattering problem. It's just that this picture that they plunge in is too simplistic. What happens is that there is a Schwinger model here. They create a phi meson, and the outgoing state will have this topological surface. And there is a small centrifugal barrier, not as big as for the KK modes, so they don't quite make it all the way, but they make it much closer than the KK modes. Yes. So you could say that phi is just reflected and there is nothing to discuss. But if you look at the version which has an f, so remember that this boundary condition, if you just take an f equals 1 and little n equals 1, there is no problem with the scattering. And the resolution is on this slide. So instead of having this boundary condition on the monopole, it's wrong. You just have put this, phi vanishes and scatters off in a trivial fashion. So there is no scattering puzzle for little n equals 1 and f equals 1. But when you increase little n or an f, the scattering puzzle still appears because this mechanism doesn't gap out all the modes. This VEV doesn't gap out all the modes. It leaves a smaller number of modes than the index theorem, but maybe eventually they're also gapped out by quartics, but at the moment we don't know. Right. Yes. So it's not presently known, in my opinion, how many modes actually survive. I showed you that just in the minimal case, none. I wrote here a small comment at the last slide. I'll get to it in a second, Tim. So I think that this discussion doesn't affect the fact that quantum numbers which are exotic have to come out in the scattering experiment, but it shows that the counting of the zero modes certainly must be revisited. So let me just summarize everything I told you. We saw that there are anyons and a whole state that trails the radiation in a scattering from a monopole. We discussed this unitarity puzzle in 1+1 dimensions, and this is the comment about Tin's question. You can ask, do symmetries perhaps protect some of these fermion zero modes? And the answer is, in my opinion, when an F is bigger than 1, yes. When an F is bigger than 1, some fermions will be protected from getting mass from quartics. But for an F equals 1, I don't know of an argument that protects any of the zero modes. This is my current understanding. So when an F is bigger than 1, because there is this chiral symmetry that is inherited from 4D, there will be a few fermions that must survive, much smaller than the number of the fermions in the index theorem. But when an F equals to 1, I don't have an argument that any fermion survives. Kind of. You're asking what is the origin of the anomaly, two-dimensional anomaly of RCNF? Yeah, it's because as Thomas said, the left-moving SUNF is involved in a two-group in the four-dimensional theory. This leads to a 't Hooft anomaly in the dimensional reduction on the monopole background. Yes. So I'm saying for me at the moment, in my opinion, it's an open question. But for n equals 1, I think I gave you the answer. What is true? Well, then how do you reduce with a fixed monopole charge? The problem seems to make less sense then. In particular, the magnetic field can be screened. You cannot even fix the value of the magnetic field. Okay, thank you so much.
I mean, let's put it in the framework of supersymmetric monopole.
Yes.
How it goes.
Yes. I don't know, but you can ask if yes, I understand. You can ask if in the supersymmetric theories the zero modes are protected.
Yeah.
I honestly do not know the answer. But let me see. I just honestly don't know the answer. I know that in the supersymmetric literature, people have claimed that there are fermion zero modes around BPS monopoles, and it better be correct. It better be correct. So I'm tempted to say that probably this doesn't happen in supersymmetric theories, but I don't really know why. I haven't tried to write the effective Lagrangian and understand why the Schwinger model doesn't gap out the fermions then.
You should explain how it goes, right? Transition.
It's probably, I think probably, I mean, this Lagrangian is just describing the bosonized zero modes coupled to the gauge field fluctuations. In the supersymmetric theory, I guess there will be, well, I don't have something smart to say, but I assume somehow it will be avoided. Otherwise, a lot of literature will end up being wrong. Ah, yeah. I see. Out of place, yeah. Arkady, I don't even know the answer for this QED, massless QED. So first, get the answers. I mean, I don't know the answer for higher monopoles. How many zero modes actually survive? Well, maybe. Yes.
And the law was there, or,
There are no zero modes. It's wrong.
so that's wrong.
Yes. You see that there are no zero modes. You plug little n equals 1. There is no zero mode. You just generate a new scale, which is E over RS2. And there are no, I mean, no, but he's saying the effective field theory. People took the monopole, they analyzed the effective field theory. There is the Rabbi, it's called Rabbi Jakiv or something. It's just not, there are no zero modes. What can I say? There are no zero modes. They are repelled from the fermion. They're repelled from the monopole because of this effect. The J squared is E squared. Yeah, J squared is E squared over pi.
I want that we can take is square equal to minus pi to try to go to the solution. Remember, it was 1 plus is square divided by pi.
Yes.
I wonder about is square equal to minus pi.
No, the limit where you recover Georgia, the limit where you recover the literature is E squared over pi equals 0.
Yeah.
Because then B becomes a defect operator of dimension 1, and therefore there is a family of defects where you integrate the operator B.
It's really a range, I believe.
I'm
I will type it.
okay. I haven't thought about it. You see, these 't Hooft lines cannot end because they are charged under a magnetic one-form symmetry. That was the context of my papers on the 't Hooft line, so I haven't thought about this question because they cannot end on any object. Okay, thank you.
Zohar, the whole semi-classical procedure of quantizing a solid